Okay, so if all right, so if E is a set which contains part of, oh sorry, so which contains part of its boundary, then the closure of E will contain all the boundary points. Okay, so E is here. So that is the closure. Now we will introduce the concept of connectedness, right? A set E, right, in the complex plane C is called connected. Okay, if E cannot be the union of two non-empty subsets, A and B, such that the closure of A intersects B is equal to the empty set, and A intersect with the closure of B is also an empty set. Okay, so the definition of connectedness is by means of the that means that that E cannot be an union of two subsets, right? With this property, which means that if a set E is an union of two subsets A and B, such that the closure of A disjoint from B and the closure of B is disjoint from A, then E will not be connected. Okay, so that the definition is in a negative way. It's not in the positive way. Okay. All right, and so I would like to state a lemma, right, which says that an open set in C in a complex plane is not connected. Okay, if and only if it is the union, okay, of two disjoint non-empty open subset. Okay. So it's very important that we are saying that an open set is not connected if only if it is the union of two disjoint non-empty open set. Okay. All right. Before I move on, So do you have any question about the definition of connectedness? Oh, okay. All right. Maybe before, okay. I take an example here. Right. So this is A and this is B. And if E is equal to A union B. Okay. Right. So suppose E is a subset which is union of A and B. Okay. Here. Then of course E is not connected. Okay. The reason is that A and B are already closed set, so that so the closure of A is equal to A itself, right? And the closure of B is B itself. So now we find two subsets A and B, and A and B are disjoint. Okay, so that so there exist two subset A and B such that this is true, right? So that so clearly E is not connected because there exists two subset. So the existence of A and B says that E is not connected. Okay, so in this case, so E is not connected. Right. Okay. The other is that let me say here. Okay. This region. E. Okay. Here. Then E is connected. Then E is connected. Even though these two parts is joined by a point here, right? The intersection, but E is connected. The reason is that you can't find A and B, okay, such that E is the union of A and B. All right. So if you try, right? If you try, for example, if you try okay, if you try to find so that without the intersection, this part, we say this is A, and the B is with this point, and also this part. Okay. So of course E is equal to A union B. Okay. And here with A is equal to this part. Oh, sorry. Except this point, okay? So it is here, okay? So A does not contain this boundary point, only one boundary point, but it contains all other boundary points. And the B is equal to Okay, so B is already closed. All right, and the point, the boundary point here, we will call it P. Right. So P is here. So it includes the boundary point P. But P is here, right? So A does not include P, point P. Now you can see that A bar intersects B is equal to P, which is not empty set, right? Because the closure of A contains A and all its boundary points. Okay, so A, right? So that for this case A and B, right? Even though we know E is the union of A and B, but the closure of A intersects B is not equal to even though A intersects B bar is E intersects B is the empty set. So even though A intersects the closure of B is empty set, but the closure of A does not is not disjoint from the B. Okay. Okay. So AB is not the choice. Okay, and if you want to find other way, okay, so so you will get into a trouble. Okay, so you will get into trouble, and so to prove that E is connected, you have to use the contradiction that suppose you have an AB, subset AB, with this property, all right, and you will render a contradiction, right? And so it takes some time. So I don't want to do it right now, but you can try at home, okay? So with this definition, to show a set is connected, the common approach is by using contradiction to assume the existence of two subsets AB satisfy these properties, and with that assumption, then you get a contradiction, and then so that shows that no such pair of AB exists. Okay. And to show a set which is not connected, you just find. So usually you do it by construction. So you find two subsets, two non-empty subsets AB has this property. Okay, and then for just like this case, right? And you can show that the E is not connected. Okay. Other questions? So I have said this shows that A and B are not the choice. Okay. And a rigorous proof. Okay. Can be established by the proof of contradiction. Okay. All right. Okay, and the lemma, the lemma shows that an open set. Okay, so the opens. So you can see to use the definition to show the connectedness. Sometimes it's hard because you have to use the proof of contradiction. Okay, but so it's better to deduce some useful theorems, right, for common practice, right? And the first lemma here is a good one, right? Because that if you consider open set, then an open set is not connected if and only if it is the union of two disjoint open set. All right, but it's still from the negative part, right? And so to show an open set which is connected, you have to use proof of contradiction. Okay, so this lemma is also not so convenient, but the next theorem would be useful. Right, will be useful. Okay, so a non-empty open set omega in the complex plane is connected if and only if any two of its points, okay, can be joined, okay, can be joined by a polygon. A polygon means a series of line segment. This is not a property, but a polygon just all right, so a sequence of line segment, all right, joined at the end point, okay, which is called polygon, joined by a polygon which lies in omega. Okay. So, so this is a good theorem because it gives you the condition that to justify whether an open set is connected. So for example, if you have an open set, so E is here, all right? And you say E is connected. You can pick up 2 points, any 2 points here. So here this is P, and this is Q. All right, you have 2 points. All right, and you will see, can we connect? Can you join these 2 points by a polygon in this set, in this open set. So the polygon here is here. So you can go right. So you see yes, yeah. So from the picture, you see that any 2 points in E can be connected, can be joined by a polygon. Okay, so E is connected. Right, so E is connected. And the reason why we consider only open set, because for a cross set, this condition is not sufficient or necessary. For example, if we consider an arc or a curve like this one, okay? All right, so this is E. And this set is closed and also connected. So E is closed and connected. Right? So this arc is connected. Okay? And it cannot be justified by this condition. Why? Because if you pick up 2 points, say here, a point P here, a point Q here, we can't find a polygon. We can't. Because any polygon, a line segment, will be not contained in E, right? Not inside the E. Because it's curved, right? It's curving. So we can't apply this condition. Right? But for open set, we give a proof, right? For open set, then this condition is sufficient and necessary for this open set to be connected. Okay? Right. So that's why we have to limit the usage of this theorem to open set only. Okay? For cross set, for this cross set E here, right? This cross set, we have to go back to our definition to show that it is connected. Okay? Usually by proof of contradiction. Okay, so any questions? No. So examples of now any singleton is connected. So a point. So if a set consists of only 1 point, which means a singleton must be connected. Okay. Why? Because it is impossible. It is possible to find 2 non-empty subsets, right? With this property. Because it is only 1 point, right? So you can't find 2 subsets of this, 2 non-empty subsets, right? Because any non-empty subset is the singleton itself. Okay, so A must be equal to B. When A equal to B, then the intersection must be itself, so not empty at all. Okay. So any singleton is connected from definition. Okay, from definition. So again, we use proof of contradiction, because if there exists AB, then A, B must be equal to this set itself. And this is set, a singleton set is already a cross set, because it contains its bounded. The boundary point of this set is also itself. Okay. Now a maximal. Now a property, if E1 and E2 are connected, and E1 intersect E2 is not empty set, then E1 union E2 is connected. Okay, so if we have two connected sets, all right, so this is E1, which is connected, and even though we touch a point here, say P, this is E2, and E1, E2 is the singleton, right? And the E1 and the E2 are connected. All right? So E1, E2 are connected by themselves, right? And they have intersection, which is just a singleton. Then together, E1 union E2 is connected. Okay. Okay. So if we have so you may use a proof of contradiction. Okay, again, right? So that so if E1 and E2 is not connected, means that there exists AB, right? Right, which are subset of E1, E2, a subset of the union of E1 and E2, and having the properties here. Okay, and from that you can show that either E1 is not connected or E2 is not connected, and which is a contradiction. Okay, so that is the way to show this statement. Okay, so if we have two connected subsets, and these two connected subsets has non-empty intersection, then their union must be connected. All right. Now a maximal connected subset of a set is called a component. Sometimes some people call it connected component. of the set. So in here, E is not connected, right? So A is a component of, because it is the maximum connected subset. B is also another component. So this is say E consists of two components, A and B here. Okay, and B here. They may have a smaller connected subset, for example, here. All right, so this is C here. C here, all right, is a connected subset of E, right? So C itself is connected and is a subset of E. But C is not the maximum connected subset, okay? A is, right? And also B is another component. So a maximum connected subset is called component of the set. And the two components of a set must be disjoint. Okay, must be disjoint. Why? Because that if two components, because every component is a connected set, right? And if they are not disjoint, means that they have intersection, like this one. Then their union again is connected. Okay, and that will contradict to the maximality of component, because components are maximal connected subsets. Okay, all right. So they cannot. So any two components cannot have non-empty intersection. So they are disjoint to each other. So otherwise, okay, and other concept, and any component of an open set must be open to. This is from this lemma, because here, if an open set is not connected, right? So if it's connected, then itself is just, it has only one component. Okay, so of course, but if it's not connected, then is the union of two disjoint non-empty open subset. Okay, so if you find their disjoint subset, then every disjoint subset must be opened, and as we know, components are disjoint. Right? Right. So that so the argument is the same as lemma. Okay. Okay. Now each component, okay, each component say each open set contains a point, right, whose real part and imaginary part are both rational numbers okay, because every open set, so if we have open set here, now open set, which means that we can pick out a point, right? And a neighborhood will be inside this open set. So if U is an open set, which is open, right, and we pick up a point P, okay, so this is a neighborhood. Now in this neighborhood, we can find a point, right, whose real part and the imaginary parts are rational numbers. Okay, rational numbers there. Because that rational number extends in the real line. Okay, so and there are countably many points, all right, in the complex plane whose real and the imaginary parts are rational numbers. Okay, so from there we will see that. Okay. So the number, right? The number of components of an open set is countable. Okay. So if we have an open set, and we know every component of an open set is an open set, right? Already, and now we may ask how many components, right, of an open set we have, and we find that it is possible infinite many, but it's still countable. Okay, we can count them. Right. Okay. Now and we know non-empty open connected set in C in the complex plane is called a domain. Right? So this definition is coincide with our definition of domain before. Okay, so any open connected set is a domain, and because it's open set, so it is connected if and only if that for any 2 points we can join the 2 points by polygons. Okay, by polygons. Right? And from here, so any open set in C consists of countably many disjoint domain. Because every open set has countably many components, and each of them is an open set, right? Right. And the component is the maximal connected subset of a set. Right. So we know in the convex plane, if you talk about open set, then you know that this open set is formed by is the union of countably many disjoint domains. Okay, and each such domain is a component, right? So each component is the maximum connected set, okay? And which must be open, of course, by our previous discussion. Okay. Right. All right. So this is called the domain. Now, a simple about the path, a simple closed path, right, is a closed path, okay, gamma, whose range gamma star does not intersect or touch itself. Okay, so okay, so that if and here is gamma alpha equal to gamma beta. Okay. All right. So this, and you can see the range does not intersect or touch itself, right? So that this is simple. So this path, this cross path is simple. So a simple closed path. Another example. Okay. Right. And because it touches itself or intersects itself, so this one is not a simple closed path. Okay. So closed path can be classified as simple or not simple. Okay. It depends on that its range. Okay. So as the parameter t go up, okay, except the two endpoints, because as a closed path, then gamma alpha must be equal to beta. But in between alpha and beta, there is no two t, no two time parameters has the same, of course, map to the same point. Okay, so algebraically you can define that so you can say a closed path gamma from alpha beta to C, okay, a closed path is called, is a simple if and only if gamma t T1 not different gamma T2. For all T1 not equal to T2 with okay, T1 not equal to T2, and okay, so you can't find two parameters, different parameters, T1, T2, in this open interval, excluding the two endpoints. Okay. Well, I think this has some risk. Maybe I will say that for all T1 or T2, except, all right, except the case T2 in alpha beta, right? Except that T1 equal to alpha, except alpha okay, maybe I'll all right, except okay, so it's better. Okay, right. So that there is no intersection here. Right. So this is the definition of simple cross path. All right. Now, a simply connected domain D in the complex plane C, okay, is a domain such that every simple closed path, right, in D enclosed only points in D. Okay. So now we right. So this is a domain D. So D, right, which is the domain, and it is simply connected because that every simple cross path. So if we find a simple cross path here, So this is simple closed path. So we have here this way. And we find that this simple closed, so this is a simple closed path. Okay? So this is a simple closed path. And this is simple closed path enclosed. So enclosed points. So it enclosed, so the part it enclosed is here. Only points in D. Okay. So D is simply connected domain. Okay. Now let's show you and okay, here. Even though we cut a point, see here, just a point. Okay, cut a point. Right. So the so maybe I will. Maybe I use this is A, right? So the open disk with A and R here minus A itself. Okay, so we puncture the center, right? So this disk, this one, and this one is the domain. Okay, it's a domain, of course, because it's connected. Because any 2 points here, you can use a polygon to join them, right? So that it is a domain because it's an open connected set. But it's not simply connected. The reason is here. If you construct a simple cross path here, okay, so this is a simple closed path, right? In D A minus A. Okay, this is in D. Right. But it encloses the area, the enclosure, including 8 points, right? So this simple closed path encloses not only points in D, but also points not in this set. Okay. Okay. Which encloses point A, which is not in the set. Okay. So that this is not a simply connected domain. Okay? So that even though a disk, an open disk, is a simply connected domain. Okay? So if we consider D itself A right? This one is a simply connected domain. Right? So this open disk is a simply connected domain. But if we delete the center or any point, not necessarily center, right? If we delete any point from this disk, then it is not a simply connected domain anymore. Okay? Not anymore. Okay. And also, if we consider annualness, so if we cut a hole, right, here, if we cut a hole here, so that this is D, A, R, okay, cut the closure of A to R2, R1. Okay, so here, this is R2, R1, okay. And we contain the boundary, all right? So the disk, this is bigger, right? But minus, so we just truncate across the disk, right? Because we're including the boundary, right? Then this one is not a simply connected domain. Okay, this is not a simply connected domain. Okay. Right. So so this is some geometry about state in the complex plane. Okay, we should know about them. Okay, especially we talk about domain a lot, right? So in complex analysis, that we usually consider complex functions in a domain. Okay, and a domain actually an open connected state. So you have to know connectedness, right? So I try myself to introduce you the concept of connectedness, right? In the geometry of the complex plane, okay? And we also it is very often that in complex analysis we consider simple coarse paths, right? So we have to define what do we mean that coarse path to be simple, okay? And you have to know that if the range does not touch itself, okay, except the endpoint, right? So this is a definition in terms of functions self, okay? And finally, we need a concept called simply connected domain, okay? So that it is a domain such that such as every simple closed path in D should include only points in D, right? So that the inside of a closed path, all the points should be in D, okay? So that even though we know the open disk is a simply connected domain, but if we delete only one point from this open disk, then the resulted domain is still a domain, right? Will not be simply connected anymore. Okay, so it will destroy the simply connectedness. Okay, it is very serious in some cases. Okay, so we have to distinguish this possibility. Okay, so let's take a short break of 5 minutes. Okay, so we have several examples of simply connected domain here, and both of them are not simply domain. So they are called so any domain. So they are called multiply connected domain. Okay, so they are called multi-connected, not simply connected. All right, and sometimes we need a more precise definition. So more precisely, a bounded domain okay, so a bounded domain means a domain, right, that lies entirely in some circle about origin. Okay, it's called P-fold connected. If its boundary consists of P closed connected set, right, without common points. Okay, without common points. The closed, we say closed connected set, including such as passes and segment, or single points. Okay, so close connected set. So such as passes, segments, or single points. So for example, this is a particular close connected set, right? Okay, and so let's see. All right, so this is originally an open disk, so it's simply connected. Okay, it's simply connected, and so that the boundary, you can see there is only one boundary, right? The boundary itself is a path. Okay, so it's a closed and connected set, right? Connected set. So this is one. So simply connected means is one. If a simply connected domain which is bounded, which means that P is 1. Okay, P is 1. But for multiply connected, then P will be greater than or equal to 2. Right? So if we have 2, we deleted 2 points. Okay, or even 2 points here. So this is P1. P2, okay, so D disk A, the center is A, okay, R minus P1 and P2 here. So now this one, because it's bounded, right? It's bounded. So this is threefold. It's a threefold connected domain, right? Because whose boundary including the circle, okay? So including the circle, including the boundary of the disk, right? And P1 and P2. Okay, so it consists of three, right? This is the boundary, right? So this is the circle here, right? Circle is what boundary, and P1 another boundary, P2 another boundary. So 1, 2, 3, right? So it's threefold. Okay, it's threefold. Okay, it's threefold here. Okay, and okay. So this one, this D, is D, right? So this D is also a threefold connected domain because it consists of three closed paths as boundary, right? So this is this one and this one. Okay, so it has three, right? 1 and 2 and 3, right? Whose boundary including three disjoint circles. Okay, including circles. So it's threefold. It's threefold connected domain. Any questions? Okay, now I state the main theorem of this section, Cauchy's integral theorem. Okay, in a simply connected domain. All right, so D. All right, D is a simply connected domain. P, a point in D, and the F is continuous on D and analytic, right, in D minus P. right? So then the line integral, right, over gamma is 0 for every simple, right? So gamma should be simple closed path. Gamma in D. Okay. So now we have a version for simply connected domain. And a convex open set, right? Note that a convex open set, right? We stated in the previous theorem, in theorem. Okay, in theorem 14.2.3, all right. So a convex open set is a simply connected domain. Okay. Right. And convex open set, we mentioned that in theorem 14.2.3, right? So instead of a simply connected domain in that theorem, we consider some special kind of simply connected domain, which is called convex open set. All right. So convex open set is a simply connected domain, and in there, the conclusion, right? We can exclude a point, and a function is continuous on a convex open set, and analytical in the convex open set, except the point P, right? And in that case, the line integral here is 0 for every closed path, not only simple. Okay? So, but if we extend the domain to simply connected domain, so simply connected domain is wider, a wider class than convex open set. Okay? So this is more general, but the closed path should be simple. Okay, should be simple. So the conclusion is here, right? We have 0 line integral, okay, for every simple. So that you have to know that we require the closed path to be simple. Okay. All right. So I hope you know the difference and different applications in the 3 Cauchy integral theorems. So we stated 3 versions of Cauchy integral theorems here. All right. Now, and the Cauchys, okay. So now the Cauchy integral theorem lay a foundation of the useful Cauchy integral formula. Okay, all right. So now gamma is a closed path. Right? So omega is equal to the complex plane, but without gamma star. Okay? So that, okay. Now, since gamma star is a compact set, it is closed, right? So that its complement. So that its complement omega is open. Okay. So this is an open set. Okay. Right. Any questions? Any questions? Gamma star is complex, means that it is bounded and closed. Okay, so it is closed. Okay, and its complement, so the omega, and the define. So we now define a complex function. Right, IND gamma z. Okay, so it's a complex function. Right, 2 pi I, and the line integral gamma eta minus z, and the d theta. For all z in omega. The reason why this complex function can only define on this open set omega is because that because this rational function here, if z is a point on the gamma star, then this function, this integrand, is not defined. Okay, it's not defined. So as we know by our definition, so this is okay. So this is integral. And if this closed path going through z, then this is 0. Okay? So if this is a complex plane, this is our complex plane here. Right. And gamma is a closed path. Okay, so this is gamma star. Okay. And we define the index function, IND, is for every point, z here. Okay, so z cannot be on gamma star. Okay, cannot. Okay, right. But for any z outside of gamma star, then this function is well defined. And we give a name, so which is called the index, okay, of point z in omega, okay, with respect to the cross path gamma. Okay, so that's why we put gamma as the subscript here. All right, so this is the index of the point z with respect to the cross path gamma. Okay, and so this index exists. Okay, exists for every point z in omega. omega. Okay? All right. So this is well defined because this is a continuous function. Okay? This is a continuous function here. Okay? A continuous function of t, and this is a continuous function of t. All right? Piecewise continuous, right? And so the integral has final value. Okay? So you can evaluate this one. Okay. All right. Now, the index function IND gamma z, okay, is continuous. Okay, it's continuous on omega. Okay, first of all. As shown in the lecture notes. Right. So you can see the detail of the proof. All right. So this is a continuous function. Okay, it's a continuous function of that. Now, Stale's theorem. And called the winding number our index of a point. Oh, by the way, sometimes we call index, but sometimes we call the winding number. Okay. These two terms are exchangeable. So sometimes people call this as the index because IND, right? But sometimes it's called the winding number, and we will see the meaning later. So the winding number or index of a point with respect to a closed path. All right. All right. So this theorem tells us some basic property of the index function. Okay, so gamma across the path. Okay, omega is the C. So it's the complement. The complement of gamma star in C. Okay. So now then the index function IND gamma z, okay, is an integer valued function on omega, which is constant. Okay, so which is constant in each connected component component of omega, and which is 0 in the unbounded component. Okay, so let's see here. The omega, so the omega is the complement of gamma star. Now the omega is open set, as we see from previous discussion. Any open set, all right, any open set consists of countably many open components, right? So how many components do we have in omega here? The unbounded component here, 1, right? And this is another component. This is another component. This is another component. And this one. So how many components do we have? 5, right? There are 5 components. Okay? So there are 5 components of this omega. Right? And so that so this is unbounded. So we said D here. So D, maybe we say it's D0. This is D1, D2, D3, and D4. Okay. So that omega is D0 union D1, D2, D3, D4, and the Di are component of omega. Okay, so they are components of omega. They are components of omega. And the index function, according to the theorem here, D0 is the unbounded. So this one is the unbounded component of omega. Okay, so index in this here, so index, so in here with index which is 0. Okay, so the winding number are set, and we have to give the, so this go this way. Right. So this is the orientation, all right? So this is the orientation here. And all the points Z in this unbounded component has index of winding number to be 0. Okay? So it's 0. And the index, which is in the integer value function, and it's a constant in each component. So all the points in D1 has the same index. Okay? They have the same index here. All the points in D2 have the same index here. And all the points in D3 has the same index here. And all the points in D4, okay, has the same index. And all the index are integers, so it may be minus integer or positive integers. Okay, some can be -1, -2, -3, -4, etc. Can be 1 or 2 or 3 or 4, etc. Okay, so this is the meaning of this theorem. Yes. Yeah, 0. Oh, yes, can be 0. Yes. Yes. Okay. And for unbounded component, the index value must be 0. But it is possible that D2 may be 0. Yeah, the index is 0. It's possible. That's true. Okay? That's true. Right. So this is the fundamental theorem to characterize the index function. Okay, so it's amazing, right? Because that it is such a line integral here. Okay, and of course we use spatial integrand here. It's 1 over eta minus z. Okay, for any fixed z here. Okay, but it's amazing that this line integral should be an integer. Okay, should be an integer here, right? Integer. And I have give a remark. So please see the remark. Okay. So please see the remark after this theorem to understand why we call as the winding number of z with respect to gamma. Okay, right? Because the winding means that for a point here, now the cross path will wind, right? So it's we're winding there, but outside in here we have one winding, right? But in here we have no. Okay, so now there's no effect, but so that so you can see it is going through rounding points. Okay, right. And so please see the remark to see that. Okay, and so this is a quantitative theorem to describe the key feature of the index function. And the next theorem gives us a mean to actually calculate the index. Right. So this is stated. Okay. All right. So gamma is a cross path. Okay. And now, suppose that we have two parameters, u and v, in between alpha and beta, because this interval is the domain of this cross path, and B is a complex number with the modulus R, which is greater than 0, which means that B is a non-zero complex number, and 1 gamma u is equal to A minus B. Oh, I forgot. A, B. So we have 2 points, A, B in C, with, all right, B, all right, is non-zero. And gamma of V is equal to AB plus B. The second, gamma of S minus A, this thing R, if and only if U is in this interval. And the 3, gamma S minus A equal to R, if and only if S equal to U or S equal to V. Okay, so that we have this situation. Right. Now assume furthermore that the open disk minus gamma star is the union of 2 domains. Okay, D plus and D minus, right, labeled. So that A plus BI is in the D plus, the closure of the D plus, and A minus BI, okay, is in the closure of D minus. Okay, so as gamma T traverses the open disk from A minus B to A plus B. Okay. Then D minus is on the right. Okay, and D plus, okay, is on the left of the path. Okay, then the conclusion. Okay, maybe I write here. Okay. Okay, then the index gamma of Z equal to 1 plus index gamma of W. If Z is in D plus and W is in D minus. Okay. So that is the situation. So let me write down here. Okay. Let me show you. All right. Mm-hmm. Okay. We have so this is the left and right. Okay. D plus, D minus. Okay, and here is gamma V is gamma U, which is A minus B, A plus B. Okay, all right. And is this then? Okay, so if we can find A here, let's see. So it's B. Now, okay. So it's R. Yeah. Okay. Center is A here. Okay. Okay. So you see that this is the situation. If we can find a disk, so this is the disk of A. Okay. Now, if it travels and the D D minus is in the on the right. Okay, so if we travel, this is the right, right? And D plus is the left here. Okay. Now, if we have a point W here, and we have a point Z here. Okay. Oh, this is W. Okay. So we have two parts. So this is D minus, and the other parts. This is D plus. Okay. Now the index here. So the index, right, of our points in D plus is 1 plus index of W here. So now we can apply the theorem to see here. We know the unbounded component has index 0. Okay. Now, for D4, because the point in D4, it will traverse, right? And this is left, this is right, this is left. So the index here will be equal to 1 in D4. Okay, because on the left has index 1 more than the index on the right. Okay, so this is 1 here. This is 1. Okay, and when we go this way, so this is when we go D2, right? So this is the right, and this is the left. And this is 0, so the index here is -1. All right? It's -1. And how about here? We go, this is the right, this is the left. Okay? Right. So, and the left. Okay, so this is -1 too. Okay. And we go this way. Right. So this is the right, and this is the left. So we have 2 here. Oh, first of all, you can see you go right this way, and this is the right, right? If you think about this, D4 is on the right, and D3 on the left, right? And on the left has more index, right? Has 1 plus the index on the right. Because this is Z is in the D plus is on the left. D minus on the right, right? That's here. D minus. So if you when the path travels through this disk, right? So you locally see the disk, and then you go up, and then this part is D minus because it's on the right, and this on the left, so it's D plus. So D plus has 1 more index, the 1 in number, than D minus. So if this is 0, then this is 1, right? And if this is 0, then this is -1, right? Because we have this equality. Okay. All right. So we know D4 is 1 already. Now, how about D3? D3, so we look a local point here. Oh. A disk here, right? Now, D4 is on the right, and D3 is on the left. So that index on the left is 1 more index on the right. So this is 2. Okay, this is 2. So now we have 0, 1, 2, -1, and the -1 here. Okay, so if we look at here, okay, so when we go up, so this is right, and this is left, right? So left is higher, right? But the left is 0, index is 0, so the right is -1. Okay? All right. So the theorem here is very technical, but it's very nice for you to identify which component has which index, which 1D number. Okay, and so it's easy for you to justify. And then with these two theorems, A and B, now you are able to compute the index function. Okay, the index function for any closed path gamma. Any questions? Okay, so I stop here.